All right. Hopefully, I don't know. Let's see the audio. The audio. 1, 2, 3, 4. Let's plug 1.5. Let's try this again. Yeah, USB. Okay, looks good. Let's 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3. Okay, it's good. Sounds good. All right. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Good, good, good. All right. So I don't have much time because I need to go out and should go out. I should start getting ready at most, I would say, in 15 minutes. So this is just going to be the beginning. We have a lot of work because I don't know how to do this. I don't know if anyone has ever done this. This is a new thing. We're going to try and derive the Einstein's postulate of constant speed of light from first principles, from the assumption of ether. So we're going to take the assumption of ether, but it's not just an ether. So we're going to try and derive the postulate about wave mechanics, that in any wave system, in any wave system, in any wave system, the speed of the wave is constant to all inertial observers in that wave system, assuming they all have clocks that are based on the medium at hand. So it doesn't matter. It's not only for ether, it's for any medium. So in your bathtub, let's draw the postulate. I don't believe that no one has ever done this. I mean, that's impossible. Someone must have done this. Okay, so create new. All right, so it's going. This is going to be proving constant speed of wave, constant wave speed, or just constant wave speed. That is the postulate. That's Einstein's postulate of special relativity. So special relativity sits on top of this postulate. So if we can prove the postulate, then it's no longer a postulate. It's no longer an assumption. If we can derive the assumption from something, then the assumption is no longer an assumption, and the underlying assumption that leads us to the postulate of the constant speed of light becomes the new assumption. And that assumption is going to be a medium, namely ether. So this should be proof of ether in of its own. This by itself should be proof of ether. And again, I'm not changing relativity. I'm just completing, I'm adding another bottom layer. I'm adding a foundation. I'm adding one more layer of foundation to Einstein's relativity. Let's go. Let's do this. I don't have much time. Nevertheless, I will give you a link to my Discord. If you want, you can join me. I drank a second cup of coffee, but I gotta go. But still, I'm very tired. I don't know why I'm so tired this day. This day specifically, really tired. All right, let's go. So, what are we saying? We are saying that in a bathtub, in any medium, it doesn't matter what the medium is. It doesn't matter. Any medium. Some medium. The dots is some medium. It's some medium. Water, air, ether, whatever. So you can make a wave, right? You can tap, you can destabilize, perturb the medium, and create usually waves in all directions. You can create waves. So let's say these are waves in the bathtub. These are water surface waves. All right. So given that and given a clock, this clock is just going to make a perturbation. It's going to create a wave, and it's going to touch the other side, and a detector. This is the design of our clock. A detector will detect the wave and will reply with another wave going the other way, and boop, whatever, and again and again and again and again. All right, that's the clock. This is very similar to Einstein's photon clock. But as we said many times, the photon clock doesn't make any sense. Instead, it needs to be a wave clock. In Einstein, it should have been a light wave clock, as per Young's experiment that light is a wave. Also, Maxwell, light is a wave. So Einstein knew light is a wave. I don't know why he talked about waves as photons. Doesn't make any sense. So as a wave, we know that waves in a medium, from experience and from symmetry and logic, we can say that the speed of the wave c is a constant. That is it's not even a postulate. I mean, I think this is everyone agrees. I mean, if I would claim that this is, I can't say it's I didn't discover this. I mean, right? Because of the mechanics, we understand wave mechanics. We understand that how waves work. So waves depend on the mass of each particle, the force of interaction between particles, the average distance between the particles, or something like that. These are the water, whatever. It doesn't. I'm not going to go into wave mechanics, but because of, I would say, symmetry, the speed of waves is a constant. So that is assumption, the assumption, right? So, but right, we're going to prove this for a water, a tub with water. This is our sandbox. This is where we're going to prove our theory that for all inertial observers, and here is an inertial observer. An observer is a clock. A clock, just like this one, that works on the principles of waving the medium back and forth. That is an observer. So any observer is going to look at any waving or at any propagation of a wave and is always going to measure c, a constant, the same constant c. It's not going to change. I don't know how no one has ever proved this for a bathtub. I don't know how Einstein didn't prove this first for a bathtub. Has anyone, am I really the first one to prove this? I don't believe it. But I looked it up before. No one gave any proof ever that, right? Because no one has ever thought that no one has ever defined this clock to be an observer. This comes from Dialect's video, where they show that they can derive Lorentz transformation and time dilation if we assume a sound clock. Now we can assume a sound clock, but why not a bathtub? Even simpler than a sound clock. Now this clock, somebody can produce and sell these clocks so that people can play with them in high school or at home. You can play with them. Now this clock notice with this clock, of course, notice, immediately you get from this clock, you get time dilation instantaneously without even trying. So this clock, if you move it through the medium, let's say the medium we're assuming is stationary. If you now drag this clock through the medium while it's on, so as it is bouncing, now I'm going to stop drawing all these waves. Instead of these waves, I'm just going to pretend it's just like Einstein photon, or, I'm just going to draw a straight line. So this is the line, boop, and the line back, boop. That's one tick or two ticks, whatever. So notice that since, right, the way the clock works is it sends a wave on the other side and then it's quiet. It sends, let's say, one wave and then it's quiet. On the other side is a detector. The detector detects the wave, the perturbation, and in response, it replies and it replies. Now, on the first side, there's also a detector that detects the incoming perturbation and sends again a wave to the other side. So there is a detection, reply, detection, reply, right? So in the beginning, when you start the clock, it sends the first wave without first receiving a reply. But after that, it reacts, both sides react to an incoming perturbation. And you can make this like a very advanced clock with maybe you can send actually some encoded wave or something, but let's keep it simple for now. Okay, now notice that you get time dilation as soon as you move this clock. Let's say you move it to here, and further you move it to here. So as you move it, it's the wave is going to travel sideways, and by the time it hits the other detector, right, it traveled sideways. So obviously, when the clock was standing still relative to the medium, the ticking was fast. As you now move with velocity v inside the medium, the ticking slows down. And here's the next tick. So the ticking has slowed down. And Dialect has shown that T prime is equal to T original divided by gamma, where gamma is the Lorentz gamma, which is the square root of something like 1 minus V over C squared. So this is true in the bathtub. So immediately you get time dilation. Okay, so now if you assume that this is our brain works on these waves, right? Just like in reality, our brains are based on light, because all the particles that make us up move at the speed of light. But they move at the speed of light, but because of the Higgs mechanism, they slow down. But ultimately, they slow down, but they don't slow down. They appear to slow down. They just interact. They bounce back and forth, but they are moving at the speed of light. But really, it's just they're waving. The reason it looks like, I mean, they're not moving at the speed. I mean. Anyway, so if we assume that that we have a brain, like we have a robot, whatever, we have a human, whatever, that their brain, their perception is this ticking. This ticking is the very consciousness of a creature. Then this creature's consciousness has slowed down. This is time dilation. The clock ticking is the consciousness. It has slowed down because of motion through the ether through the medium, through the water. So the consciousness is slowed down. All right, the next step is to determine how this clock now measures the speed of any wave. Meaning, we need to prove that this clock always measures the constant speed of light, the same constant speed of light. So as long as the observer, this is the observer, this clock, this is the observer. It's always when it measures the speed of light, the speed of waves in the medium, it's always going to measure the same c. C is a constant. Okay. Okay. I don't know how to do this, and I'm surprised I'm the first person in history to do this, but it's not exactly my forte, but I'll do the job, I'll take the case. I'll take the case. As Harry Birdman says, I'll take the case. All right, but I gotta go. So I'm just going to, if anybody wants to complete this work, that'd be nice. But, okay, so this moving observer, so we can just say Mr. A, this is the clock, is let's say it is moving, observer A is moving at velocity v, and let's say that it is, okay, we need it to observe, right, Mr. B, clock B or something, or B, we need it so A needs to see the waves created by B or something. Or you know what? Let's start it easy. Let's start the waves going away from A. So as A moves faster and faster, right? Let's forget about B for now. So A is moving, and the waves, right? The waves are moving at speed c. Let's say A is making waves, and these waves are moving forward, of course, at c. But A is moving at v. So, right, if A was a boat, if A were a boat, then A wouldn't see C moving at C. Sorry about the double meaning. It's a tub. We're not at sea. So A would not measure the speed of the waves moving away from it. Right? So let's say A didn't see the shore of the bathtub. And let's say it's dark. A is not aware of its motion. Right? A cannot be, let's say A is not aware of its motion. So A doesn't know that it's moving at V. But A is making waves, and A can either see the waves, or maybe there is a mirror here and A can measure the time, whatever. Let's say A is looking at these waves. We'll simplify it. A is looking at these waves. It's not seeing the waves, right? If A were a boat, A would not see the waves moving away from it at speed c, because A is moving at v, and the speed of the waves is c relative to the bathtub, to the water, to the medium. So if A were a boat, it would see these waves moving at c minus v, of course. But A is not a boat. Indeed, in reality, there are no boats. There are no particles. There are only waves. So as A as a wave, as a waving clock, because when it's moving at V, its internal consciousness has slowed down. It is experiencing time dilation. Its brain has slowed down. It's imagine the diagonal of because of v. Because of this slowing down of the brain, even though the waves are moving away from A at c minus v, but A's perception must be slowed down so that A still perceives these waves moving away from it at c, at speed c. This is what we want to prove. If we can prove this for any medium, we have proven Einstein's postulate of the constant speed of light. We no longer need Einstein's postulate. This is a significant accomplishment. This is not insignificant. All right. Let's think about how we're going to prove this. So, well, how does A, right? So A needs to do the measurement. So A needs to say that the speed of the wave, right? So A is looking at the speed of the wave, moving away from A. The speed of the wave, as A measures it, is some distance as measured by A, right? So A measures, well, this wave C has moved a certain distance over a certain time. So let's say the wave moves, right? It has moved. Let's say this initial wave, let's go to green color. So let's say A is going to measure, let's say this motion of the wave. And this we're going to call D. This is the distance that the wave has traveled. But this is, I mean, there's already a problem because I think A experiences length contraction. So A is not going to, I don't know what it means for A, right? A cannot measure because A's, I don't know. Anyway, we know from our point of view, let's talk about our point of view, and then maybe we can switch the frame of reference to A. From our point of view, this wave, we're talking about this wave. This wave has traveled distance d relative to the bathtub over time t relative to the bathtub. The velocity of the wave, now we at the bathtub, we know this is c. We also know the question is, what does A measure? So does A see the distance d? That's a good question. What kind of distances, because A's perception has changed, because it's a moving target. The wave is a moving target. I don't know what A is seeing. We know that it's experiencing time dilation. I never looked at the development of the equations for length perception or the length contraction. The question is A experiencing a shorter bathtub? Is the entire bathtub now shorter because A is experiencing not just time dilation, but also length contraction? Right? Because how would A measure the distance? The only interaction A has with the universe is through these waves. Its perception is these waves, and anything it wants to detect, it has to do with the wave, just like we do with light. So so what is, let me get a sip of water and then I gotta go. So we know, right? So a in order to learn about distance, it has to. So what is this distance? I mean, A is not aware of this distance. It cannot be aware of the distance. So what A could do is set up, I mean, what would A do? I mean, I would say, I don't know. This is so confusing. I haven't played enough with time dilation. Time dilation, I understand, but length contraction. Maybe I need to play more. I didn't play at all with length contraction, and I really have to go. I really need to go. So, but I need to think about this. I need to think about it. Maybe I'll take a piece of paper and a pen to where I'm going, and I'll just sit and do this work. I don't have even paper and pen. I have a pen. I'll just grab a piece of paper where I go, and I'll just sit and develop these equations. They should be very simple. I mean, this we could test it, but right, the question is, from A's point of view, how fast is this wave moving away? What does it mean away? What does it mean away? I guess what I would do is I would say before A starts the experiment, A sets up a distance. Like part of A's clock would be, or A's boat would be a mirror, and A is firing the wave at this mirror and is expecting the wave to return. So A must know this distance. This is A's laboratory. So A knows this distance. Now, as A, right, and this, okay, so this should move with A. This lab will move with A. So it's going to appear to A to not, it's not going to be a moving target. So this distance is going to be the same distance because it's in A's reference frame. So A is going to take his lab with him. And in the lab, he's going to have this mirror. This is akin to a person in a rocket ship in a moving frame of reference. Inside, he's enclosed inside this moving frame of reference, inside a rocket ship, whatever, inside a train. He's enclosed. He doesn't know he has his distance, his laboratory. His laboratory hasn't changed. It's moving with him. It's stationary. He doesn't know. So he measures distance d. He doesn't have an issue measuring distance d. And he's going to measure c. We know that he's going to measure c because is in his own frame of reference. So of course he's measuring c. He's going to measure d and c and his own t. And the t is going to be such that t divided by d is equal to c. So t, this is going to be prime because we're looking, prime means a. So t over d prime is equal to c. C No, we don't know that. This is what we don't know. So we say it's equal to C prime. We don't know. We don't know this. This is what we're trying to prove. So A, with his own consciousness slowing down, he's going to measure a time, right? He's going to fire a pulse of surface level water wave. He's going to fire it at his mirror in his lab. His lab shares the same motion of water, the same medium. So this mirror is not blocking the medium. So A is going to fire this wave. It's going to hit the mirror and come back. So it's going to be 2D. So the time, let's say 2t, the time that A measures, t prime, 2t prime, there and back again, over the distance that A perceives, which is d prime, because is his frame of reference. We don't know what happens. We as the observers, right? We are the observers, but as the observers, we also can only view A Can we? Are we able? Maybe we are able to look at A in any way we want. I would have to think about that. Okay, I gotta go. Okay, this is really confusing. Really confusing. I don't know. I mean, Einstein was really brilliant. Okay, let's see. Carlos says if the waves are circular, then T prime over D prime is equal to C. T prime over D prime is equal to C. But we're trying to prove that it's going to be the same C. It's not so clear. So C prime, we know that it's C minus V. We know that it's not C. But anyway, it's confusing. It's confusing. We're trying to prove, at the end, we want to prove that C prime is equal to C. Whatever speed of the wave A measures, and whatever speed we measure, we know it's always C. I mean, we're not moving. We're part of we're the experimentors. So we know C is constant. A doesn't know. A expects it to be, but he cannot assume it. This is what we're setting out to prove. So we would need to think about this, but I gotta run. So I'm gonna stop here. So I'll see you next time. Bye for now.